ionization energy. To form a positive ion, an electron must be removed from a neutral atom. This requires energy. The energy is needed to overcome the attraction between the positive charge to the nucleus and the negative charge of the electron. So this is like the ionization energy. So what do you mean of ionization energy is defined as the energy required to remove an electron from a gaseous atom. Okay, so to form positive ion we have to what? To remove electrons or one electron for example from what? From the neutral atom. So we need energy to remove this or to overcome the attraction force between the positive charge of the nucleus and the negative charge of the electrons. So this energy is needed is defined as the ionization energy, which is the energy required to remove an electron from a gaseous atom. For example, 8.64 times 10 to the power of negative 19 joule is required to remove electron from gaseous lithium atom. Okay, so for example, this is the ionization energy to remove one electron from a gaseous lithium atom. Okay, the energy required to remove the first outermost electron from an atom is called the first ionization energy. So the energy required to remove the first outermost electron is called as what? It's called as first ionization energy. For example, the first ionization energy of lithium equals 8.664 times 10 to the power of 19 joule. The loss of the electron results the formation of what? Because we remove only one electron, so it will be Li positive 1 ion. This is the first ionization energies of the elements in periodic 1 through 5 are plotted on the graph in figure 17. So this is the first ionization energy of elements in period from 1 to 5, as you know, to lose only one electron. Okay, so this is, for example, for helium. This is the first energy for helium, and this is the first energy of the ionization energy, sorry, for hydrogen, the ionization energy of neon, and this is the ionization energy for lithium. So the first energies for elements in period 1 through 5 are shown in this as a function of the atomic number. So first ionization energy versus the atomic number. So the first ionization energies for elements in period 1 through 5 are shown as a function of the atomic number. Each set of connected points on the graph represents the elements in a period. Okay, so these are the elements in the period, in the same period. Okay, so for example, H and He, they are in the same period. Li and Ne, they are in the same period. Na and Ar, they are in the same period. Okay, first ionization energies generally increases as you move from left to right across what? Across a period. So as you move from left to right across a period, the increased nuclear charge of each successive element produces an increased hold on the valence electrons. So again, the first ionization energy generally increase as you move from left to right across what? The period. So as you see, we have in the same period Li, then Ne. Look how Ne has more for first ionization energy from Li. So as you move from left to right across the period, the first ionization energy will increase. The increased nuclear charge of each successive elements produce the increased hold on the valence electrons. The group 1 metal Li, Na, K and RP indicates the green tags. So these are elements in green. They are in the first group. These are the elements in the first group. So thus group 1 metals are likely to form positive ions, as we know that group 1 they are form positive 1 ions. The group 18 elements indicates the blue tags. These in the blue, these elements He, Ne, Ar, Kr, and Xe, they are the elements in group what? In group 18. Okay, and they are unlikely to form ions, as we know that in group 18 they are stable, so they don't form ions. The stable electrons configuration of the group 18 elements greatly limits their reactivity. That's why the ionization energy for group 18, they have a very high first ionization energy, because they are they unreactive. Okay, they are inactive. So as you move down a group, the first energies generally decrease because atomic size increases. Less energy is required to remove the valence electrons further to the nucleus. So as you move down a group, the first energies generally decrease. Okay. The ionization energy. Think of ionization energy as an indication of how strongly an atom nucleus holds onto its valence electrons. So to think about ionization energy, you have to think it as how strongly the atoms hold their valence electron. Okay, a high ionization energy value indicates the atom has a strong hold on its electrons. Atoms with large ionization energy values are less likely to form positive ions. Likewise, a low ionization energy value indicates an atom's losses on an outer electrons easily, such as atoms are likely to form positive ions. Lithium, for example, has low ionization energy, for example, because it is important for its use in lithium-ion computer batteries, where the ability to lose electrons easily make a battery that can quickly provide a large amount of electrical power. Each set of connected points on the graph figure 17 represents the elements in period. The group 1 metals have low ionization energy, thus group 1 metals Li, Na, Kr, are likely to form positive ions. Group 18 like He, Ne, Ar, Kr, Xe have high ionization energy. They are unlikely to form ions. The stable electron configuration of gases of group 18 greatly limits their reactive, as we said that. Okay, so again, high ionization energy means atom has a strong hold on its electrons and atom is likely to form a positive ions. Low ionization energy means atoms loses on outer electrons easily. Atoms is more likely to form positive ions. Removing more than one electron. After removing the first electron from an atom, it is possible to remove additional electrons. So if you remove the first electron from the atom, it is possible to remove what? A second electron. The amount of energy required to remove the second electron from positive one is called the second ionization energy. The amount of energy is removed, the third electron, positive 2 ion, is called as a third ionization energy, and so on. As we will see in this table, it lists the first through ninth ionization energies for elements in period 2. So the energy needed to remove the first electron is the first ionization energy. To remove the second electron, it's the second ionization energy. To remove the third electron, it is the third ionization energy, and so on. And these are values of the first ninth ionization energy for elements. For example, lithium, Be, carbon. As you see, as the number of electrons you removed from the atom, okay, so the ionization energy will increase. Okay, so the first ionization energy, for example, 800, the second 2400, the third is 3600. As you see here, the amount of ionization energy needed to remove more electrons is increasing. Okay, so reading across table 5 from left to right, you will see that the energy required to form each successive ionization always increases. However, the increase in energy does not occur smoothly. Not that for each element there is an ionization for which the required energy increases dramatically. For example, the second ionization energy of lithium, 7,300 kilojoule per mole, is such greater than its first ionization energy, which is the 520 kilojoule per mole. This means that a lithium atom is likely to lose its first valence electron, but extremely unlikely to move its second electron. If you examine again table 5, you will note also that the ionization at which the large increases in energy occurs is related to the atom's number of valence electrons. The element lithium has one valence electron, and the increase occurs after the first ionization energy. Lithium easily forms the common lithium positive 1, but it is unlikely to form lithium positive 2. The increase in ionization energy shows that atoms hold onto the inner core electrons much more strongly than they hold onto the valence outermost electrons. Okay, so as you see in figure 17 and by the value in table 5, first ionization energy generally increase as you move from left to right across the period. The increased nuclear charge of each successive element produce an increased hold of the valence electrons. First ionization energy generally decrease as you move down the group. The decrease in energy occurs because atomic size increase as you move down the group. Less energy is required to remove the valence electron farther from the nucleus, and this is the periodic table. Again, the ionization energy decrease as you move down on the same group, and increase as you go to the right on the same, and increase as you go from left to right in the same period. Okay, now octet rule. When a sodium atom loses its single valence electron from a positive 1 sodium ion, its electron configuration changes as shown below. Sodium atom 1s2, 2s2, 2b6, 3s1. Sodium ion this is the sodium atom, but sodium ion once you lose one electron will be 1s2, 2s2, 2b6. Okay, note that the sodium ion has the same electron configuration as neon. So if you so it has how many valence electron? It has 8 valence electron. This observation leads to one of the most important principles in chemistry, which is the octet rule. Octet rule means the octet rule states that atoms tend to gain, lose, or share electrons in order to acquire a full set of 8 valence electrons. So the atoms always tend to lose, gain, or even share electrons. Why? To have a full set of 8 valence electrons. So this reinforces what you learned earlier, that the electron configuration of filled s and p orbital of the same energy level consisting of 8 valence electrons is unusually stable. Note that the first period elements are an exception um, um, to the rule, so because they are completely with only 2 valence electrons. So this is the octet rule and the ionization energy trend. When a sodium atom, for example, loses its single valence electron to form positive 1 sodium ion, its electron configuration changes, as you see here. Once this sodium lose 1, so its valence electron will change to have how many valence electron we have here? 8, okay, according to the octet rule. So again, ionization energy is defined as the energy required to remove an electron from gaseous atom. The energy required to remove the first electron is called the first ionization energy. Removing the second electron requires more energy, which is called the second ionization energy, and each successive ionization requires more energy, but it is not a steady increase. First ionization energy increases from left to right across a period. First ionization energy decreases down a group because the atomic size increases and less energy is required to remove an electron farther from the nucleus. The octet rule states that the atoms tend to lose shared electrons in order to acquire full set of 8 valence electrons. The first period elements and the second period metals are an exception to the rule. They are stable when they have just 2 valence electrons in the first orbital. Okay, and we have these questions. Please answer them. Rank the following atom in order of decreasing first ionization energy. So rank them or arrange them. Use the periodic table, and these are the answers.